Hello viewers, welcome to our YouTube channel. This is Vennila from Department of ECE, King's College of Engineering, Punalkalam. In this video, we are going to see the topic Hilbert Transform, Pre-envelope and Complex envelope, which is in the subject Communication Theory for BE ECE 4th semester students. Hilbert Transform. First, we will see the idea behind the Hilbert Transform. Performing the Hilbert transform on a signal is equivalent to a 90-degree phase shift in all its frequency components. Therefore, the only change that the Hilbert transform performs on a signal is changing its phase. The amplitude of the frequency components of the signal do not change by performing the Hilbert transform. On the other hand, since performing the Hilbert transform changes cosine into sine, the Hilbert transform x dash of t of a signal x of t is orthogonal to x of t. Also, since the Hilbert transform introduces a 90-degree phase shift, carrying it out twice causes a 180-degree phase shift, which can cause a signed reversal of the original signal. Next, we will see in detail about the Hilbert transform. So, what is Hilbert transform? If every frequency component of your signal f of t is shifted by minus pi by 2, the resultant signal fh of t is the Hilbert transform of f of t. So, this is the phase shifting system, that is minus pi by 2 phase shifter. Minus pi by 2 phase shifter is nothing but a 90-degree phase shifting system. Here, the input signal f of t is passed through a phase shifting system h of omega. Then you will be getting the output fh of t, where fh of t is the Hilbert transform of f of t. Similarly, if we pass a signal f of w through the phase shifting system, we will be getting the output as fh of w, where fh of w is nothing but the Hilbert transform of f of w. There are some characteristics of the system that are specified under this. Number 1, the magnitude frequency components present in f of t remains unchanged when it is passed through the system, that is h of omega will be equal to 1. And the second point, the phase of the positive frequency components if shifted by minus pi by 2, since the phase spectrum omega has an odd symmetry, the phase of the negative frequency component is shifted by plus pi by 2. So, h of omega and omega are plotted here in the following diagram. So, this is the transfer function for a 90-degree phase shifter. So, in this plot, for plus pi by 2, it is going in the reverse direction, that is for minus direction, and for minus pi by 2 it is going in positive direction. So for plus pi by 2 the f value will be less than 0, and for minus pi by 2 the f value will be greater than 0. Next we will see the transfer function. The transfer function is given by the expression h of omega, which is equal to mod h of omega into e power j theta omega, which is equal to e power j h omega. Have this expression as number 1. So from the figure we can tell the theta of omega will be equal to, for negative frequencies, right, for that is for plus pi by 2 the omega value will be less than 0, and for positive frequency, that is minus pi by 2, omega value will be greater than 0. So equating this relation. Otherwise, we can rewrite the equation 1 as h of omega is equal to e power minus j pi by 2 for omega greater than 0 and 1 into e power j plus pi by 2 for omega less than 0. Otherwise, we can write h of omega will be equal to minus j for omega greater than 0 plus j for omega less than 0. So equivalently, this h of omega will be equal to minus j signum of omega. Where this signum of omega is the familiar signum function, it is defined as signum of omega will be equal to 1 for omega greater than 0 and minus 1 for omega less than 0. So we have to have it in our mind, plus pi by 2 for omega less than 0 minus pi by 2 for omega greater than 0. So this is the plot for signum of omega. So from this we can write h of omega will be equal to minus j signum of omega. Have it as our expression number 2. The response fh of omega of the system is related to the signal f of omega as fh of omega will be equal to f of omega into h of omega. Have it as equation number 3. Now we are going to substitute the value of h of omega in equation 3. So substituting the equation, so we will be getting fh of omega will be equal to f of omega into minus j signum of omega. Have it as expression number 4. So taking the inverse Fourier transform on both the sides, we will be getting fh of t is equal to f inverse of minus j f of omega into signum of omega. So the time domain of signum of omega is given by j by pi t is equal to signum of omega, and f of t will be equal to f of omega. So using the time convolution function, fh of t can be written as minus j f of t into j by pi into t. So fh of t will be equal to 1 by pi limit minus infinity to plus infinity f of tau divided by t minus tau into d tau. The inverse Hilbert transform is given by fh of t will be equal to minus 1 by pi limit minus infinity to plus infinity fh of tau divided by t minus tau into d tau. So using this inverse Hilbert transform, the original signal f of t can be reconstructed from fh of t. Here the function f of t and fh of t are considered to constitute a Hilbert transform pair. It produces a plus 90 degree phase shift for all negative frequencies and minus 90 degree phase shift for all positive frequencies. Now we will discuss about the properties of Hilbert transform. So first one, a signal f of t and its Hilbert transform have the same magnitude spectrum. Second point, a signal f of t and its Hilbert transform sh of t have the same energy density spectrum. Third point, if the Hilbert transform of fh of t is minus f of t, then fh of t is Hilbert transform of s of t. That is, if Hilbert transform of f of t will be equal to fh of t. Hilbert transform of fh of t will be equal to minus ft dash, where h is nothing but the Hilbert transform. Fourth one, a signal f of t and its Hilbert transform fh of t are mutually orthogonal over the time interval minus infinity to plus infinity. That is, limit minus infinity to plus infinity, f of t into f h of t into dt will be equal to 0. And the last one is a signal f of t and its Hilbert transform f h of t have the same autocorrelation function. So these are the properties of Hilbert transform. Next we will move on to applications. So what are the applications of Hilbert transform pair? So it is used in the generation of SSB signals. It is used in the design of minimum phase type filters. It is used in the representation of bandpass signals. So far we have discussed about the Hilbert transform. Next we will move on to pre-envelope. Pre-envelope or analytic signal. So the concept of pre-envelope is also known as the analytic function, and it is useful in deriving the general expression of SSB-SE signal. The pre-envelope of a real signal x of t is the complex function. So fp of t will be equal to f of t plus j fh of t. Here fh of t is the Hilbert transform of f of t. The pre-envelope fp of t is a complex valued signal. The real part of fp of t is f of t and the imaginary part of its Hilbert transform is fh of t. The complex conjugate of the pre-envelope is denoted by f star p of t. It is given by the expression f star p of t will be equal to f of t minus j fh of t. So what is the difference between these two equations? So first one is the complex function, second one is the complex conjugate of the pre-envelope. So it is given in the negative. So minus j fh of t. The pre-envelope is useful in treating bandpass signals and systems. This is due to the result, this fp of v will be equal to 2x of v for v greater than 0, and for v equal to 0 the x of 0, and it will be 0 for v less than 0. Next one is complex envelope. The new quality based on the analytic signal called the complex envelope. It is defined as f of t is equal to f dash of t into e power minus j 2 pi fct. By taking the Fourier transform, f of omega will be equal to 2f into f plus fc for f greater than 0 and f of 0 for f is equal to 0 and 0 for f less than 0. So the complex envelope is just the low pass signal part of the analytic signal. The analytic low pass signal has been multiplied by the complex exponential at the carrier signal. Thank you all. For more educational video, please subscribe our YouTube channel. Thank you. Thank you for watching this video.